Okay, let's take a look at the rocket sled simulation by the physics classroom to see the effect of forces on motion. Now notice the sled is not moving right now, but there are still two forces acting on it. They're labeled here. The weight of the sled pushes down, and the normal force from the ground pushes up. The sled doesn't move or accelerate or anything because these forces are exactly balanced. They cancel out. So right now we can see that there can be forces applied to an object and still no changes in motion, as long as they're balanced. If we apply an unbalanced force, let's say turn on the sled's rocket, there's now a 50 Newton applied force, and notice what's happening to the velocity. It's increasing, and it's increasing at a constant rate. So it's not a force that causes our object to move, this force causes our object to speed up, to increase its velocity, to accelerate. So let's see what happens when we remove that force again. If there are no forces, as there are now, there's no net force, that is, the velocity is staying constant. This is what objects do when there's no net force on them. They travel at a constant velocity. The sled is in equilibrium right now. And this is an illustration of Newton's first law of motion. If there's no outside net force, an object will travel at a constant velocity. So last thing we can do is we can stop the sled. We need to apply a backwards force to slow it down. Now notice we have a backwards force, but we're still moving forwards. But our acceleration is in the negative direction because our velocity is going down. It's in the same direction as our applied force. We could slow our rocket down even with the forward force if we turn on friction and air drag. Now notice there are two backwards forces and one forward force. But it's the net force that determines whether or not, or how quickly we slow down or speed up. Now our net force is 0 again. We have a 10 Newton applied force from the rocket and a negative 10 Newton frictional force, and so we don't move. So the keys here are objects at rest stay at rest if there's no net force. A net force causes an acceleration in the direction of the net force. And objects in motion stay at a constant velocity if there's no net force. Okay, so it's the net force that determines how an object moves. It's not any individual force, it's the total from all the forces. We write the net force as sigma F or F net. This is the Greek letter sigma, and it means the sum of. But it's since force is a vector, it's the vector sum of, so we just have to take into account the signs. So let's take a look at two free body diagrams. They're kind of messily drawn, and find the sum of the forces in the x and the sum of the forces in the y direction. So here we have 20 newtons to the right, 12 newtons to the left. When we do sigma F in the x direction, it's just going to be 20 newtons minus 12 newtons equals 8 newtons. In the y direction, sigma Fy, it's going to be 13 newtons up, 13 newtons down, so minus 13 newtons equals 0 newtons. There's no net force in the vertical direction. Let's do the same over here. Sigma F in the x direction, well, we have 60 newtons to the right and 60 newtons to the left. They cancel, so the net force is 0. In the vertical direction, we have 40 newtons up, 30 newtons down, so sigma Fy is going to be 10 newtons up. And I should have labeled the direction of the force over here in the x direction, 8 newtons to the right, since I didn't clearly define that right was positive and up was positive. Usually we pick the positive direction just to be the direction of the net force to make it easier. Okay, so we can summarize everything that forces do to objects with Newton's second law of motion. Net forces cause accelerations. The more net force we have, the more acceleration we get. So we say they're proportional to each other. This right here is the sign for proportional to. Acceleration is proportional to net force. And we know more massive objects don't accelerate as much. More mass is more inertia, which means less acceleration for the same amount of force. So acceleration is inversely proportional to mass. It's proportional to 1 over mass. And if we combine those together, we get that the acceleration of an object is equal to the net force divided by the mass. This is called Newton's second law of motion, and it's usually written as F equals ma. But remember, it's the net force that's equal to ma, not any individual force. So now if you know the forces, you can figure out accelerations, and of course if we know accelerations, we can use kinematics to figure out everything about an object's motion. This is going to be our problem-solving strategy when we're dealing with forces problems. We're going to use free body diagrams in Newton's second law to figure out accelerations, forces, etc., and basically all of our unknowns. So here we have a situation to the right. A 20-kilogram box is pulled across a rough floor. If the force of friction is 70 newtons and the applied force is 95 newtons, find the acceleration of the box. We're not going to worry about the numbers just yet, but we will later. But here's our strategy. Draw an accurate free body diagram with labeled forces. And we want it to be a simple diagram. Set the direction of the acceleration to be positive. So we're going to say right is the acceleration, which means right is positive, because our applied force, notice, is bigger than our frictional force. List our given variables. Write what we're trying to find. In this case, we're trying to find the acceleration. Here's the important part. We need to write out the sum of forces equations for the x and y directions. That is Newton's second law for the x, Newton's second law for the y. So let's do that for this situation here. Sum of forces x equals ma x. Well, in the x direction we have the applied force to the right, F applied, minus the frictional force to the left, equals mass times acceleration in the x direction. In the y direction, we have the normal force pointing up, so we would say Fn, gravity pointing down, so the force of gravity, or mg, equals, well, we know there's no acceleration in the up-down direction, so mass times acceleration is just 0, equals 0. And then we just solve for our unknown variables. In this case, we want to find ax. We could plug in our numbers and solve for that. Let's do another example. A rocket sled is on horizontal ground. Its thrusters are on, and friction and air drag are not negligible. So let's sketch out a free body diagram and set up the laws of motion equations. Rocket sled has thrusters, which apply a thrust force forward. We know since it's on the ground, there's going to be a normal force up. And we know that gravity is going to be pulling down, force of mg. Since it's not accelerating up, down, it's on the ground, normal and mg should be about the same size. We have two backwards forces, force of drag from the air and the force of friction. We don't know which one's going to be bigger. I'm just labeling them like this. The way I've drawn my forces, my rocket sled is slowing down, so the acceleration is going to be to the left. So let's set up sigma f x equals max. Since a is to the left, left is positive, so we do friction plus drag minus thrust equals mass times acceleration in the x. That's our law of motion equation. And in the y, we just have normal minus the force of gravity, and since there's no acceleration, no net force vertically, it's 0. That's it. Plug in our numbers and we can solve for all kinds of things. One more example. A car in neutral gear slides down a hill. So this is a little bit more complicated because our car is on a hill, so I'm going to draw the hill. There are going to be at least two forces acting. Downward force of gravity, mg, and an upward force, well, it's not upward, a normal force from the ground that points perpendicular to the ground, normal force. Now, since our car is sliding down the hill, the velocity is down, I think the acceleration is also going to be down that hill. We're going to say that this is, the direction of the acceleration is going to be the positive x. So I'm going to say this is positive x, and this is y. Normal is in the y direction. Gravity is not in either the x or y direction, so we just have to break it into components. So we would write this as mg sub x, and the y component as mg sub y. Now we can set up the laws of motion. Sigma Fx equals max. In the x direction, we have the x component of gravity, mgx equals mass times acceleration in the x. And we could use trig to figure out what that actual component is. In the y direction, it's not moving into the ground or off the ground, so it's just going to be normal force minus mgy. Since there's no acceleration in y, it's equal to 0. The normal force is equal to the y component of the gravitational force. That's all. Hope that was helpful. Bye.